Hello, my name is Gilles Oudebrouckx. I'm an electrical engineer and researcher at Hasselt University, Belgium. Today I would like to present to you our novel method of measuring thermal conductivity of liquids inside a microchannel. We call this method the Transient Thermal Offset method. But before I start explaining this method and before I start to discuss how we validated the accuracy of our prototype device, I would first like to take some time to convince you of the importance of measurements of thermal conductivity.
To understand why we are so interested in measuring thermal conductivity, it is important that you know that a value of thermal conductivity is more than just a boring material property. A value of thermal conductivity can tell you more about a sample than only its ability to conduct heat. For instance, diamonds have a very high thermal conductivity, and based on the measured thermal conductivity, it is possible to decide if a diamond is real or fake. Another interesting use of a value of thermal conductivity is in milk. Researchers have shown that the thermal conductivity of milk can be used as an indicator of the fat content. Another study has already shown that a reading of thermal conductivity can be used to determine the concentration of cell suspensions. These last two examples bring us closer to the topics of today's lecture, microfluidics and biosensors. Because with our presented method, similar experiments can be performed inside a microchannel on small liquid samples of less than 3 microliters. Furthermore, this technique might be used in the development of thermal-based biosensors. Our method is derived from a well-known method for measuring thermal properties of various materials called the Transient Plane Source method, which is illustrated here. A TPS sensor generally consists out of a thin substrate on which a metal structure is deposited. The structure can be used as a heater by sourcing an electrical current to it. Simultaneously, the temperature of the structure itself can be monitored by measuring the voltage over the structure to detect the temperature-induced change in electrical resistance. Both heating and temperature sensing can be achieved simultaneously via the 4-wire measurement principle. The thermal properties of the sample can be derived from the slope of the transient curve. However, when working with small samples, such as liquids inside microchannels, there can be a problem concerning the thermal probing depth. We provide a solution for this problem by using a highly thermally conductive material for the top of our microchannel, such as aluminium. We will intentionally apply thermal pulses that probe beyond the boundaries of the microchannel, inside the top material. By doing so, we can use the top material as a reference to eliminate issues concerning probing depth. To predict what our transient curves will look like, we have developed a Cauer thermal equivalent circuit of the sensor device. In this equivalent circuit, each layer of the device is represented by an object with a certain thermal resistance and a certain thermal capacity. During a measurement, the thermal properties of the substrate and top reference will be constant at all times. The thermal properties of the microchannel will depend on the fluid that is inside the channel. We generated SPI simulations of this circuit. Hereby we chose realistic values for the thermal properties of the substrate and top reference, based on the materials used in our prototype sensor design that is discussed later. When we vary the thermal resistance of the fluid while maintaining a constant thermal capacity, we can see that all transient curves are perpendicular at the end, with a slope that is determined by the thermal properties of the top reference. It is clear that variations in thermal resistance cause a change in offset at the end of the transient pulses. When we vary the thermal capacity of the fluid whilst maintaining a constant thermal resistance, we can see there is no influence on the offset at the end of the transient pulses. Therefore, we assume that values of thermal conductivity can be derived from the offset at the end of the transient pulses, hence the name, the Transient Thermal Offset method. To test this measurement principle in practice, we have developed a prototype sensor design that you can see here. In order to explain how the microfluidic device is built, we are going to take it apart and put it back together. We put the device together upside down, so we start off with the aluminum top. This is a piece of aluminum of about 4 cm by 5 and it has a thickness of 6 mm. Apart for the 4 holes provided for the screws, there are 2 small holes present for the fluid inlet and outlet of the microchannel. On top of the aluminum, we place our microchannel. The microchannel is cut out of a piece of parafilm using a cutting plotter. On top of the microchannel, we place our sensor. The sensor is incorporated on a flexible PCB. The polyimide substrate is 40 micrometers thick. On this substrate, a copper-resistive meander structure is present, with 4 connectors to enable a 4-wire measurement. By applying heat, we seal the microchannel between the aluminum and the polyimide. To prevent the flex PCB from flexing, we add an acrylic backplate for a rigid back support. We use 4 screws to hold everything together. Let's have a closer look. Here you can see the resistive copper meander structure of overall 5 by 1.3 mm. Here in red, we see the elliptical shaped microchannel that is placed around the sensor structure. We assume that only the fluid inside this area is being measured. Therefore we say that with this device, measurements of thermal conductivity are performed on samples with a volume of less than 3 microliters. When having a look at the top of the device again, we can see that there are 2 holes present for screw-type tube fittings for the inlet and outlet of the microfluidic channel. This is what the sensor device looks like in practice. When we have a look at the backside of the device, we can see that it is transparent. We can see through the acrylic backplate as well as through the yellow polyimide sensor substrate. So far, we have only discussed the microfluidic device. Now we will discuss the other required hardware that we have used to obtain the results presented in our paper. In this picture, you can see the complete measurement setup. As you can see here, for the experiments presented in our paper, we have daisy-chained 4 microfluidic devices. This way, each device will measure the same liquid sample. And by comparing the results of different devices, we can get an idea of the reproducibility. To flush different liquid samples through our microfluidic devices, we use an automatic pumping setup. To demonstrate the working principle of our device and to determine the accuracy, we decide to flush different water-ethanol mixtures through the microchannels. We choose for water-ethanol mixtures because water and ethanol have very distinct values of thermal conductivity. The mixtures were prepared in advance and were flushed through the devices with static periods of 15 minutes in between each pump step. Meanwhile, we apply thermal pulses via our pulsed 4-wire measurement approach. The pulses of 30 milliwatts have a duration of 16 seconds and a cooling period of 80 seconds. The heating time is chosen to ensure that the probing depth of the thermal pulses reach into the aluminum top reference. The longer cooling time ensures that the sensor cools back down to room temperature. When we plot all the voltage curves resulting from these thermal pulses on top of each other, we can already see the influence of the ethanol concentration on the offset at the end of the thermal pulses. We perform a linear curve fit in the marked time interval on each heating curve and plot the offset of the fit as a function of the start time of the applied heating pulse. From this plot, we can clearly derive the different pump steps that were applied. As you can see here, you can see the times at which different water-ethanol mixtures were flushed through the flow cell. In between each flush containing ethanol, we flushed in pure water to ensure that our sensors have a constant baseline. When we add the data of sensor 2 to this plot, we can see that the result is reproducible. However, when looking at the data coming from sensor 3, we can see that the offset value is higher in general for the entire measurement. For sensor 4, the offset value is lower for the entire measurement. We have two possible reasons for this shift. The first reason is the difference in electrical resistance of the different sensor structures that were used. A second reason can be that there is a slight variation in the height of the flow cells that have been used. To eliminate this variation, we suggest normalizing the data relative to a measurement step in water. After doing so, it can be seen that the result is similar for all sensors. In order to obtain a calibration curve for our sensors, we first select the normalized offset data from 10-minute time intervals. Next, we obtain the values of thermal conductivity of the different used water-ethanol mixtures from literature. From now on, we will call the literature values the actual values of thermal conductivity. When we plot the selected normalized offset values as a function of the actual thermal conductivity, we can find an exponential relation. We can use this exponential equation to convert the measured offset values to values of thermal conductivity. These converted values are what we call the measured values of thermal conductivity. When comparing the measured values with the actual values of thermal conductivity, we can conclude that the presented devices have an accuracy of 1% and a standard deviation of 11 milliwatts per meter Kelvin. We can conclude that our presented method for measuring thermal conductivity in microchannels is simple and straightforward. Issues with probing depth are eliminated, and the method allows for further miniaturization. I hope I could have inspired you to consider measuring the thermal conductivity of your samples to get new insights. Thank you for your attention.